Tonight, we're going to explore one of the most violent transformations in the entire universe. Imagine an object so dense that a single teaspoon of it weighs more than 1 billion tons. An object that packs more mass than our entire sun into a sphere smaller than a city. That's a neutron star. Now here's the part that should stop you in your tracks. This impossibly dense remnant of a dead star has a limit. There is a threshold of mass beyond which even the most extreme form of matter known to physics cannot hold itself together. Cross that line, and the neutron star doesn't just collapse, it stops existing as matter entirely. What replaces it is something far stranger, a region of space-time from which nothing can ever return. And the journey from survival to annihilation is far more complex than anyone expected. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with what a neutron star actually is. Because before we can understand how one can be destroyed, we need to understand what keeps it alive. And by alive, I mean what prevents it from collapsing under its own unimaginable weight. A neutron star is what remains when a massive star dies. Not a star like our sun. Our sun is too small to create one. When the sun eventually exhausts its fuel, billions of years from now, it will swell into a red giant, shed its outer layers, and leave behind a white dwarf, a dense remnant certainly, but relatively gentle, about the size of Earth, still recognizable as matter in a form we can at least partly relate to. A neutron star comes from something far more violent. It comes from a star at least 8 to 10 times more massive than our sun. These enormous furnaces burn through their nuclear fuel not in billions of years, but in mere millions. They live fast, they burn hot, and they die in one of the most powerful events in the known universe, a supernova. Here's what happens inside one of these massive stars as it approaches the end of its life. Throughout most of a star's existence, there's a balance. The energy released by nuclear fusion in the core pushes outward, creating pressure that holds the star up against the inward pull of its own gravity. For millions of years, these two forces exist in equilibrium. Gravity pulls inward, fusion pushes outward. The star remains stable, but fusion doesn't last forever. A massive star fuses hydrogen into helium in its core. When the hydrogen runs out, it fuses helium into carbon and oxygen, then carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each stage burns faster than the last. Hydrogen fusion might last 10 million years. Helium fusion, a few million. Carbon fusion, perhaps 1,000 years. Oxygen fusion, maybe a year or two. Silicon fusion lasts about a single day. And then the process stops, because iron is the end of the line. Every element lighter than iron releases energy when it fuses into something heavier. That's what powers a star. But iron is different. Fusing iron doesn't release energy. It absorbs energy. It's an energy dead end. When the core becomes a ball of iron roughly the size of Earth and about 1.5 times the mass of our sun, fusion ceases. The outward pressure that has been holding the star up for millions of years simply vanishes. And in that instant, gravity wins. What happens next takes less than a second. The iron core, which has been holding up the entire weight of the star above it, collapses. Not slowly, not gradually. It implodes at speeds approaching 1/4 of the speed of light. In roughly 1/10 of a second, a ball of iron the size of Earth crushes itself down to a sphere about 20 kilometers across. That's roughly 12 miles, about the width of a mid-sized city. The outer layers of the star, now completely unsupported, come crashing down onto this ultra-dense core and bounce off it. This rebound, energized by a staggering flood of subatomic particles called neutrinos, tears the star apart from the inside out. The explosion is almost beyond description. For a few weeks, a single dying star can outshine an entire galaxy containing hundreds of billions of suns. The outer layers are hurled into space at tens of thousands of kilometers per second, scattering heavy elements that will eventually become part of new stars, new planets, and potentially new life. But the core remains, crushed, compacted, transformed into something unlike anything else in nature. During the collapse, temperatures and pressures become so extreme that the normal structure of atoms is destroyed. Protons and electrons are forced together, merging into neutrons through a process called inverse beta decay. What was once a ball of iron atoms becomes a ball of almost pure neutrons, packed together so tightly that the entire mass of the core, more than the mass of our sun, is compressed into that sphere about 20 kilometers across. That is a neutron star, and the fact that it exists at all, that it doesn't simply collapse further into nothingness, is one of the great puzzles and triumphs of modern physics. Let's talk about the density for a moment, because the numbers here are genuinely difficult for the human brain to process. A neutron star packs roughly 1.5 to about 2 times the mass of our sun into a sphere about 20 kilometers in diameter. The density of this object is roughly 100 trillion times the density of water. Imagine taking our entire sun, all that mass, all that material, and crushing it down into something you could fit inside the boundaries of a small city. That's what happened here. And the result is a density so extreme that nothing in everyday life even begins to compare. If you could scoop out a single teaspoon of neutron star material and bring it to Earth, that spoonful would weigh roughly 1 billion tons. 1 billion tons in a teaspoon. The Great Pyramid of Giza, one of the largest structures humans have ever built, weighs about 6 million tons. A teaspoon of neutron star material would outweigh roughly 160 Great Pyramids. All of that mass contained in a volume smaller than a sugar cube. You could hold it in your hand if your hand could somehow support the weight, which it absolutely could not. Nothing on Earth could. The gravity at the surface is equally extreme. If you dropped an object from a height of just 1 meter above a neutron star's surface, it would hit the ground traveling at roughly 7 million kilometers per hour. On Earth, the same object falling from the same height would land at about 16 kilometers per hour. The neutron star's surface gravity is roughly 200 billion times stronger than what you feel standing on Earth right now. If you somehow stood on the surface, which you could not because you would be flattened into a film of atoms thinner than a sheet of paper, you would weigh about 200 billion times what you weigh right now. The escape velocity from a neutron star's surface ranges from roughly 140,000 to over 200,000 kilometers per second. That's somewhere between about half and 2/3 of the speed of light. To escape Earth's gravity, a rocket needs to reach about 11 kilometers per second. On a neutron star, you'd need to go more than 12,000 times faster. And even then, the extreme curvature of space-time near the surface means that general relativity plays a major role in how objects move, how light bends, and how time itself flows. Clocks on the surface of a neutron star would tick roughly 20 to 30% slower than clocks far away in empty space. Time itself is warped by the extreme mass concentrated in such a small volume. This is not a normal object. This is matter pushed to the very edge of what the laws of physics allow to exist. And the question we're really asking tonight is simple but profound. What happens when you push it past that edge? So what keeps a neutron star from collapsing further? Why doesn't all that mass or that crushing gravity simply squeeze the star down to nothing? This is where the physics gets truly fascinating, because the answer involves some of the deepest principles in all of science. The first and most fundamental source of support is something called neutron degeneracy pressure. This is a quantum mechanical effect, and to understand it, you need to know about one of the most important principles in physics, the Pauli exclusion principle. In 1925, an Austrian physicist named Wolfgang Pauli discovered something remarkable about the subatomic world. He found that certain types of particles, called fermions, absolutely refuse to occupy the same quantum state at the same place at the same time. Electrons are fermions, protons are fermions, and crucially, neutrons are fermions. Two neutrons cannot exist in exactly the same quantum state simultaneously. It's not that they choose not to. It's that the laws of quantum mechanics forbid it. This isn't a suggestion or a tendency. It is an absolute, unyielding rule built into the structure of reality. Now think about what this means inside a neutron star. You have roughly 10 to the power of 57 neutrons. That's a 1 followed by 57 zeros, all of them crammed into a sphere about 20 kilometers across. These neutrons are packed incredibly close together, far closer than nucleons in an ordinary atomic nucleus. As gravity tries to squeeze them even closer, the Pauli exclusion principle pushes back. Each neutron demands its own quantum state. And when you compress them into a smaller and smaller volume, the available quantum states become more and more restricted. The neutrons resist. They push back. This resistance creates an outward pressure called degeneracy pressure. Here's the critical thing. This pressure doesn't come from heat. It doesn't come from chemical reactions. It doesn't come from any kind of energy input at all. It comes purely from the fundamental quantum mechanical nature of particles. Even if you could somehow cool a neutron star down to absolute zero, this pressure would still be there. It's built into the fabric of quantum mechanics itself. It's the universe's way of saying that you cannot squeeze identical fermions into the same state, no matter how hard you try. Think of it this way. Imagine a room full of people, and each person has an unbreakable rule that they must maintain a minimum amount of personal space. You can't negotiate with them. You can't bribe them. The rule is absolute. Now try to push more people into the room or shrink the room. The people push back harder and harder because they're running out of space that satisfies their rule. That's essentially what neutrons do inside a neutron star, except the rule isn't social preference. It's a fundamental law of quantum mechanics. In white dwarf stars, the smaller cousins of neutron stars, electron degeneracy pressure plays the same role. Electrons are also fermions, and their refusal to share quantum states holds up a white dwarf against gravity. But there's a limit to how much mass electron degeneracy pressure can support. That limit, about 1.4 times the mass of our Sun, is called the Chandrasekhar limit, named after the Indian-American astrophysicist Chandrasekhar, who calculated it in 1930. If a white dwarf exceeds this mass, electron degeneracy pressure fails. The electrons are forced into the protons, creating neutrons, and the white dwarf collapses into a neutron star. In a neutron star, neutron degeneracy pressure takes over. Where electron degeneracy pressure left off, neutrons are about 2,000 times more massive than electrons, which means they can resist compression at much higher densities. Neutron degeneracy pressure can support significantly more mass than electron degeneracy pressure ever could, but it too has limits, and those limits are at the heart of everything we're exploring tonight. Neutron degeneracy pressure isn't the only thing holding up a neutron star. At the extraordinary densities found deep in the core, the strong nuclear force also plays a crucial role. The strong nuclear force is the force that holds atomic nuclei together. It's the strongest of the four fundamental forces of nature, roughly 100 times more powerful than the electromagnetic force at nuclear distances. At the typical spacing found inside an ordinary atomic nucleus, the strong force is primarily attractive. It pulls protons and neutrons together, binding them into nuclei. That's why the nucleus of an atom doesn't fly apart, even though the positively charged protons inside it should be repelling each other with electromagnetic force. The strong nuclear force overwhelms that repulsion. But here's the key. At extremely short distances, shorter than the typical spacing between particles in a normal nucleus, the strong force changes character. It switches from being attractive to being repulsive. It goes from pulling particles together to pushing them apart. Inside a neutron star, the neutrons are compressed to densities 2 to 5 times greater than ordinary nuclear density, and in the deepest core, perhaps even 7 to 10 times greater. At these extreme compressions, the repulsive component of the strong nuclear force kicks in with enormous power. It provides an additional outward push that works alongside neutron degeneracy pressure to resist gravitational collapse. There may also be exotic forms of matter lurking in the cores of the most massive neutron stars. At sufficiently extreme densities, neutrons might break apart into their constituent quarks, forming a soup of free quarks and particles called gluons, known as quark matter. Some physicists have proposed that strange quarks, a heavier variety not normally found in stable everyday matter, might appear at these densities, potentially creating what's called strange quark matter. Others have suggested the formation of what's known as a Bose-Einstein condensate of subatomic particles called pions or kaons, which would have very different mechanical properties than ordinary neutron matter. The honest truth is that nobody knows exactly what happens to matter at these densities. We cannot recreate these conditions in any laboratory on Earth. The densities deep inside a neutron star core are several times higher than the densities inside an atomic nucleus, and that's the densest form of matter we can study directly. Particle accelerators like the Large Hadron Collider at CERN can briefly create temperatures and energies comparable to those found in neutron stars. But these experiments involve collisions between tiny numbers of particles, lasting for infinitesimal fractions of a second. They cannot recreate the sustained, high-density conditions inside a neutron star core, where trillions upon trillions of neutrons are packed together in a state of equilibrium lasting millions of years. Everything beyond what we can directly measure is theoretical, constrained by observations of real neutron stars, yes, but not directly confirmed. And this uncertainty about what matter does at these extreme densities is called the equation of state problem. The relationship between the density of matter and the pressure it exerts at conditions far beyond anything we can test in a lab. As we'll see, it is the reason why the maximum mass of a neutron star is not one perfectly known number. Now, here's where things take a dramatic and deeply counterintuitive turn. Because everything I've described so far, neutron degeneracy pressure, the repulsive strong force, the possible exotic forms of matter in the core, all of that is the stuff resisting gravity. Those are the forces pushing outward, fighting against collapse. But in a neutron star, gravity itself behaves in a way that Newton never imagined. And this behavior ultimately sets a hard ceiling on how much mass any neutron star can possibly support. In everyday life and in Newtonian physics, pressure simply opposes gravity. Gravity pulls things together. Pressure pushes things apart. They compete, and whichever force is stronger determines the outcome. If pressure wins, the object holds up. If gravity wins, the object collapses. Straightforward. But neutron stars are so dense and so compact that Newtonian gravity doesn't accurately describe them. You need Einstein's general theory of relativity. And general relativity introduces something profoundly strange. In general relativity, pressure itself is a source of gravity. Let me say that again because it is genuinely one of the most counterintuitive ideas in all of physics. Inside a neutron star, the pressure that is trying to hold the star up also makes the star's gravitational field stronger. Pressure, the very thing resisting collapse, simultaneously contributes to the force driving the collapse. This doesn't matter in everyday situations. The pressure inside Earth, inside our sun, even inside a white dwarf star, is so small compared to the energy density that its contribution to the gravitational field is negligible. You can safely ignore it. But inside a neutron star, the pressures are so enormous, comparable to the energy density of the matter itself, that their gravitational contribution becomes significant and eventually dominant. You're in a situation where the harder the matter pushes outward to resist collapse, the stronger gravity becomes. There's a tipping point. Below a certain mass, the equation balances. The combined support of degeneracy pressure and the strong nuclear force and whatever exotic matter might be present can hold the star up, even accounting for the extra gravity that this support generates. The neutron star is stable. It will sit there, gradually cooling, for trillions of years, longer than the current age of the universe many times over. But add more mass, push the density higher, force the pressure up, and you start running into a problem that cannot be solved. Because every increase in pressure adds to the gravitational field, which demands even more pressure to resist, which adds even more to the gravitational field. You're climbing a slope that keeps getting steeper. At some critical point, the slope becomes vertical. No amount of additional pressure can stabilize the star because every bit of extra pressure just makes the gravitational pull worse. You can never catch up. You can never get ahead. This is the fundamental reason why neutron stars have a maximum mass. It's not simply that matter runs out of stiffness, it's that the very act of resisting gravity generates more gravity. General relativity creates a ceiling beyond which stable equilibrium is mathematically and physically impossible. This maximum mass was first calculated in 1939 by 3 physicists working on 2 separate papers. Richard Tolman, working at the California Institute of Technology, published his analysis independently. At the same time, J. Robert Oppenheimer, who would later become famous for leading the Manhattan Project, and his graduate student George Volkoff at the University of California, Berkeley, published their own calculation using a different approach. Together, their work established what we now call the Tolman-Oppenheimer-Volkoff limit, sometimes shortened to the TOV limit. The original calculation by Oppenheimer and Volkoff used a simplified model of neutron star matter, treating neutrons as a cold, non-interacting gas. Under those assumptions, they found a maximum mass of only about 7/10 of a solar mass. This was a historic result, not because the number was precisely right, but because it proved that general relativity imposes a maximum mass on neutron stars, something that Newtonian gravity alone would never predict. In a Newtonian universe, you could theoretically keep piling mass onto a neutron star forever, as long as the matter was stiff enough to resist compression. Einstein's equations showed that this is not the case. There is always a point of no return, but their simplified model wasn't realistic. Real neutron star matter isn't a non-interacting gas. The strong nuclear force creates powerful interactions between neutrons, and these interactions stiffen the material, allowing it to resist compression more effectively. When you include realistic nuclear interactions in the calculation, the maximum mass goes up significantly. Modern theoretical work, using a wide range of models for how matter behaves at extreme densities, places the Tolman-Oppenheimer-Volkoff limit for a non-rotating neutron star somewhere roughly between about 2 and about 2.5 solar masses. The exact value depends entirely on which model you use for the internal physics, which equation of state you assume for matter at these extraordinary conditions. And this is the critical point. The maximum mass is not one fixed universal number. It depends on the equation of state, on what matter actually does at densities several times higher than those inside an atomic nucleus. A stiffer equation of state, one where matter resists compression more aggressively, gives a higher maximum mass. A softer equation of state, where matter yields more easily under compression, gives a lower maximum mass. The range of theoretical predictions is broad, and narrowing that range is one of the most important goals in modern astrophysics and nuclear physics combined. Observations have been enormously helpful. Over the past 2 decades, astronomers have measured the masses of several neutron stars with remarkable precision. Around 2010, astronomers measured a neutron star in a binary system with a mass of about 1.97 times the mass of our Sun, using a technique called Shapiro delay. This technique exploits the fact that light from the neutron star, which happens to be a rapidly spinning pulsar, is slightly delayed as it passes through the warped spacetime near its companion star. By measuring this tiny delay, you can calculate the companion's mass and, from the orbital dynamics, the pulsar's mass as well. This single measurement immediately ruled out many of the softer equations of state, because those models predicted maximum masses below what this neutron star actually weighs. If a neutron star exists at nearly 2 solar masses, then the equation of state must be stiff enough to support it. Any theoretical model that fails to allow a neutron star that heavy is wrong. Since then, even heavier neutron stars have been measured. Some observations suggest masses around 2.1 to 2.3 solar masses, though these values carry some observational uncertainty. Each new measurement tightens the constraints on what the equation of state can be, ruling out models that are too soft while still leaving room for a range of possibilities. Gravitational wave observations from the merger of 2 neutron stars detected in August 2017 have added yet another powerful tool, constraining how the neutron star material deforms under tidal forces, which depends directly on the equation of state. Stiffer matter deforms less, softer matter deforms more. By measuring the gravitational wave signal during the final moments before collision, physicists place new independent constraints on the equation of state. But despite all these observations, the constraints are still not tight enough to pin down one exact number. The maximum mass for a non-rotating neutron star probably lies somewhere around 2 to 2.3 solar masses, based on the best available evidence. But a definitive value remains beyond our current reach. And here's why that uncertainty matters so much. Whether the maximum mass is 2 solar masses or 2.3 solar masses makes an enormous practical difference for what happens when neutron stars gain additional mass. A neutron star born at 1.8 solar masses might be permanently stable under one equation of state and dangerously close to catastrophe under another. A remnant from a violent neutron star merger with a total mass of 2.5 solar masses might be temporarily supported by rapid rotation under one theoretical model and completely impossible to sustain under a different one. The fate of a neutron star, whether it lives or collapses into something from which nothing can escape, depends on physics we haven't fully solved. That's both humbling and exciting. We know the general framework with confidence. General relativity imposes a maximum mass. Quantum mechanics and the nuclear forces provide the support. The equation of state determines exactly where the dividing line falls, but the precise position of that line is still being drawn. It's being refined with every new observation, every new mass measurement, every gravitational wave signal that ripples through our detectors. What we do know with absolute certainty is that the line exists. There is a maximum mass beyond which no neutron star can survive in a stable state. The support that holds it up, the quantum mechanical pressure, the nuclear repulsion, all of it has a breaking point. And there are ways, violent and dramatic ways, that neutron stars can be pushed toward and across that breaking point. How they gain that fatal extra mass, and what strange forms of temporary survival become possible when they do, is where our story goes next. So a neutron star has a maximum mass. Cross that threshold, and nothing in known physics can save it from collapse. But this raises an obvious and crucial question. How does a neutron star actually gain enough mass to reach that breaking point? A neutron star is born from the collapse of a stellar core during a supernova. It arrives in the universe with a certain mass, typically somewhere between about 1.3 and roughly 2 solar masses, depending on the mass of the original star and the violence of the explosion. If it's born below the maximum mass limit, it could sit there, stable for trillions of years, cooling quietly, minding its own business. So how does it get heavier? How does an object surrounded by the near vacuum of space accumulate enough additional mass to threaten its own existence? The answer is that neutron stars rarely exist in true isolation. Most massive stars, the kind that produce neutron stars when they die, are born in binary systems. 2 stars orbiting each other, gravitationally bound, living out their lives in an orbital dance that can last millions or even billions of years. When one of those stars reaches the end of its life and explodes as a supernova, the system doesn't always break apart. The explosion might alter the orbit. It might give the newborn neutron star a violent kick. But in many cases, the neutron star remains gravitationally bound to its companion. And that surviving companion star becomes the neutron star's unwilling source of new mass. This process is called accretion, and it is one of the most important mechanisms in all of astrophysics. To understand how accretion works in a binary system, you need to think about gravity as a landscape. In a system with two orbiting objects, each one creates a gravitational well around itself, a region of space where its own gravity dominates. Between them lies a boundary where the gravitational pull from one object exactly equals the pull from the other. This boundary defines what astronomers call the Roche lobe of each object, named after the 19th century French mathematician Edouard Roche. Each star's Roche lobe is a teardrop-shaped region of space within which material is gravitationally bound to that star. As long as a star remains smaller than its Roche lobe, its material stays put. Nothing escapes, nothing transfers, but stars change over their lives. When the companion star in a neutron star binary begins to age, it may swell into a red giant, expanding enormously. If the companion's surface reaches the edge of its Roche lobe, something dramatic begins to happen. Material from the companion's outer layers starts to spill across the gravitational boundary. Hydrogen and helium pour through a narrow point between the two gravitational wells, flowing from the companion's domain into the neutron star's domain. This material doesn't fall straight onto the neutron star. Because the binary system is rotating, the infalling gas carries angular momentum. Instead of plunging directly inward, it spirals, forming a swirling disk of superheated gas around the neutron star. This structure is called an accretion disk, and it is one of the most energetic environments in the universe for its size. The gas in the accretion disk spirals slowly inward, losing energy through friction and turbulence as different layers grind against each other. As the material moves closer, it accelerates enormously, drawn by the star's ferocious gravitational pull. By the time it reaches the inner edge of the disk, just a few kilometers above the neutron star's surface, it can be moving at a significant fraction of the speed of light. The friction and compression heat the gas to temperatures of tens of millions of degrees, and at those temperatures the material glows fiercely, radiating primarily in X-rays. This is why astronomers call these systems X-ray binaries. They are among the brightest X-ray sources in the sky, easily detectable by space-based telescopes across thousands of light years. The X-ray glow of an accreting neutron star is like a beacon, announcing to anyone with the right instruments that mass transfer is underway. The energy released by accretion onto a neutron star is remarkably efficient. When matter falls onto the surface, it converts gravitational potential energy into radiation with an efficiency of roughly 10 to 20%. Compare that to nuclear fusion inside our sun, which converts mass to energy with an efficiency of only about 0.7%. Accretion onto a neutron star is roughly 15 to 30 times more efficient at generating energy than the process that powers stars. A relatively small amount of infalling matter produces an enormous outpouring of radiation. And with every gram of material that spirals through the accretion disk and settles onto the neutron star's surface, the neutron star gets slightly heavier. Not by much in any single moment, not quickly, but relentlessly. Over millions of years, a neutron star in a binary system can accumulate a significant fraction of a solar mass from its companion. Layer by thin layer, one atom at a time, the neutron star creeps toward the maximum mass that its internal physics can support. There is a natural speed limit on this process. If material falls onto the neutron star too rapidly, the intense radiation produced by the infalling matter creates an outward pressure that pushes incoming gas away before it can reach the surface. This is called the Eddington limit, named after the British astrophysicist Arthur Eddington. At this threshold, the outward radiation pressure exactly balances the inward gravitational pull on the infalling gas. Anything faster, and the radiation simply blows the material away. This means accretion is inherently slow, typically requiring millions to tens of millions of years to add meaningful mass. It is a patient process. Gravity, after all, has nothing but time, but accretion has a second consequence that turns out to be critically important to the rest of our story. As the infalling material spirals inward and lands on the neutron star's surface, it doesn't just add mass, it transfers angular momentum. It spins the neutron star up. Over time, the star rotates faster and faster, like a figure skater pulling in their arms during a spin. Neutron stars that have been spun up by accretion can reach astonishing rotational speeds, hundreds of revolutions per second. These rapidly spinning neutron stars are called millisecond pulsars because they emit beams of radio waves that sweep past Earth with each rotation, producing pulses separated by only a few thousandths of a second. The fastest known millisecond pulsars complete over 700 full rotations every single second. At those speeds, the surface of the equator is moving at roughly a fifth of the speed of light. This spin-up matters enormously, because, as we're about to see, rotation is one of the mechanisms that can temporarily save a neutron star from collapse, even after it has exceeded the mass that its internal pressure alone could support. The very process that pushes the star toward its limit also gives it a tool to survive beyond it, at least for a while. But accretion is the slow path. There's another way a neutron star can gain mass, a way that is faster, more violent, and more dramatic than anything accretion can produce. Two neutron stars can collide. Neutron star mergers are among the most cataclysmic events in the entire universe. They happen when two neutron stars, orbiting each other in a tight binary, spiral together over billions of years and ultimately smash into each other at a significant fraction of the speed of light. The combined mass of the remnant can easily exceed the maximum that any non-rotating neutron star could permanently support. And what happens in the aftermath involves some of the most complex and fascinating physics being studied today. How do two neutron stars end up colliding? It starts with gravity and one of the most remarkable predictions of Einstein's general theory of relativity: gravitational waves. General relativity tells us that when massive objects accelerate, they create ripples in the fabric of space-time itself. These ripples, called gravitational waves, spread outward at the speed of light, carrying energy away from the system. For most situations in the universe, the energy lost to gravitational waves is utterly negligible. Earth orbiting the Sun emits gravitational waves. But the power radiated is so minuscule that it would take trillions of times longer than the current age of the universe for the effect to noticeably alter Earth's orbit. But for two neutron stars orbiting each other at close range, the story is completely different. Neutron stars are extraordinarily compact and extraordinarily massive. When two of them orbit each other tightly, they emit gravitational wave energy at a significant rate, and this energy comes at a cost. It comes from the orbit itself. As the system radiates gravitational waves, it loses orbital energy. As it loses energy, the two neutron stars spiral closer together. As they move closer, their orbital speed increases, which means they radiate gravitational waves even more intensely, which drains energy even faster, which brings them closer still. It's a runaway process. a death spiral that begins almost imperceptibly and accelerates without mercy. In the earlier stages, this inspiral is extraordinarily slow. Two neutron stars separated by millions of kilometers may take billions of years to draw measurably closer. Many neutron star binaries in existence today formed billions of years ago, and are still in the early stages of this gradual inward spiral. But as the separation shrinks, the process accelerates. The final 1,000 kilometers might take only minutes. The last 100 kilometers take seconds. The very last moments play out in a fraction of a second. During those final moments, the two neutron stars are whipping around each other hundreds of times per second, moving at 20 to 30% of the speed of light. The gravitational wave emission reaches extraordinary intensity. If you could somehow translate gravitational waves into sound, you would hear a rapidly rising chirp, starting low and slow, climbing in pitch and volume, reaching a crescendo at the instant of collision. And this chirp is precisely what gravitational wave detectors have measured. In August of 2017, detectors recorded the gravitational wave signal of two neutron stars spiraling together and merging approximately 130 million light-years from Earth. The signal lasted about 100 seconds, with the gravitational wave frequency rising from around 24 cycles per second to over 2,000 cycles per second in the final moments before collision. This detection was a landmark in the history of astrophysics. It confirmed that neutron star mergers happen in nature. It confirmed the predictions of general relativity in an extreme regime never before tested. And when telescopes across the electromagnetic spectrum turned to observe the source, they witnessed a phenomenon called a kilonova. A kilonova is the burst of light and matter that accompanies a neutron star merger. When two neutron stars collide, they smash together at roughly 1/3 the speed of light. The violence is almost beyond imagination. In the final handful of orbits before contact, the two neutron stars are close enough that their extreme gravity begins to visibly distort each other. They are no longer perfect spheres. Tidal forces stretch each star toward its companion, raising enormous bulges on their surfaces. Imagine two water balloons held close together, each one pulled slightly toward the other by gravity. Except these aren't water balloons. They are objects with surfaces where gravity is 200 billion times stronger than Earth's, and even those surfaces are being warped and elongated by the tidal forces of the approaching partner. The stars become slightly egg-shaped, their near sides bulging outward as they whip around each other at dizzying speed. Matter on the surface nearest the companion star is being pulled in two directions at once, toward the center of its own star by the star's own gravity, and toward the companion by the companion's gravity. In the very last orbits, these tidal bulges become so pronounced that material begins to stream from the surface of each star, pulled outward in long spiraling tails that fling neutron-rich matter into the space between and around them. This tidal stripping ejects material before the stars even touch. It sprays matter outward at enormous velocities, and this dynamically ejected material, launched before the collision proper, carries away mass and angular momentum, and begins forging heavy elements almost immediately as it decompresses from nuclear densities into the vacuum of space. Then comes the moment of contact. The two neutron stars, each one roughly 20 kilometers across, each one containing more mass than our sun, physically collide at roughly 100,000 kilometers per second. There is no human analogy for what happens in this instant. A massive shockwave rips through the merging material. The temperature at the contact interface spikes past 100 billion degrees within a single millisecond, hundreds of times hotter than the core of any ordinary star. The pressure at the collision point briefly exceeds anything found in the stable interior of either original neutron star. Matter at the interface is compressed, heated, and violently accelerated simultaneously. The collision does not produce a neat spherical object. What forms in the first few milliseconds is a churning, oscillating, roughly peanut-shaped mass of ultra-dense fluid. The two cores, each one the compressed heart of a dead star, slam into each other and partially bounce, sending waves of compression and rarefaction rippling outward through the combined material. The remnant oscillates wildly, its shape distorting from elongated to roughly spherical and back again multiple times per millisecond. Each oscillation sends out powerful gravitational wave radiation at characteristic frequencies determined by the remnant's mass, size, and internal composition. At the contact interface itself, a splash of material is launched outward. Think of two droplets of water colliding in slow motion, and how a thin sheet of water sprays outward from the point where they meet. Something similar happens here, except the droplets are neutron stars, and the spray is a sheet of matter traveling at a significant fraction of the speed of light. This contact layer ejector is some of the fastest material produced in the entire merger, and because it comes from the hottest, most violently compressed region, its composition and the elements it synthesizes can differ from the material ejected by tidal stripping moments earlier. Within roughly 10 to 20 milliseconds, the violent oscillations begin to damp as internal friction and the magnetic field work to redistribute energy. The peanut-shaped remnant gradually settles toward a more axially symmetric shape, though it remains far from a perfect sphere. The result is a single massive body of ultra-dense matter, spinning rapidly, heated to extraordinary temperatures, with its core rotating faster than its outer layers. It is a hypermassive or supramassive neutron star, depending on how much mass was ejected, surrounded by a chaotic environment of expanding debris, fallback material, and an embryonic accretion disk forming in the equatorial plane. This is the object whose fate we are tracking. Born in violence, sustained by forces that are already beginning to fail. All of this ejected matter, whether stripped by tidal forces in the final orbits, blasted outward from the contact interface, or driven off by disk winds, shares one crucial property. It is extraordinarily rich in free neutrons. And as this expanding cloud decompresses from nuclear densities into the vacuum of space, something remarkable happens. Within that cloud, one of nature's most powerful nuclear processes occurs. Neutrons bombard atomic nuclei so rapidly that the nuclei capture dozens of neutrons before they have time to undergo radioactive decay. This rapid neutron capture process forges many of the heaviest elements in the periodic table. Gold, platinum, uranium, thorium, and dozens of other heavy elements are thought to originate primarily from neutron star mergers. The gold in a wedding ring, the platinum in electronics, the uranium that powers nuclear reactors, all of it was likely created billions of years ago in the collision of two neutron stars somewhere in the galaxy, long before our solar system even existed. The radioactive decay of these newly synthesized heavy elements powers the kilonova's glow, which can shine 1,000 times brighter than a classical nova for days to weeks after the collision. But what happens to the merger remnant itself? This is the question at the heart of our story. Because the combined mass of two merging neutron stars frequently exceeds the maximum that any non-rotating neutron star can permanently support, and what happens next depends on exactly how far above that limit the remnant finds itself. To understand the possibilities, we need to introduce three categories that physicists use to classify neutron stars based on their mass relative to the limits that internal pressure and rotation can support. These categories are not merely academic labels. They describe fundamentally different objects with fundamentally different fates. The first category is the ordinary neutron star. This is a neutron star whose total mass falls below the Tolman Oppenheimer Volkoff limit for a non-rotating object. An ordinary neutron star is permanently stable. It doesn't need rotation to hold itself up. Even if you could somehow stop it from spinning entirely, its internal pressure, the combination of neutron degeneracy pressure and the repulsive strong nuclear force, would be more than sufficient to resist gravitational collapse. This neutron star will persist, slowly cooling, for timescales that dwarf the current age of the universe many times over. It is safe. It has won its battle against gravity permanently. Most neutron stars born in ordinary supernovae fall into this category. They arrive with masses comfortably below the limit, and unless they later gain mass through accretion or a merger, they will never face the threat of collapse. The second category is far more interesting and far more precarious. This is the supermassive neutron star. A supermassive neutron star has a mass that exceeds the non-rotating Tolman-Oppenheimer Volkoff limit, but falls below a higher threshold set by rapid uniform rotation. In plain terms, if this star stopped spinning, it would be too heavy to survive. Its internal pressure alone could not support its mass against gravitational collapse. But because it is spinning rapidly, the centrifugal effect of that rotation provides additional outward support, enough to hold the star together. Think about how rotation helps. When a massive object spins, material along the equator experiences an outward centrifugal effect that partially counteracts the inward pull of gravity. The faster the spin, the stronger this effect becomes. For a neutron star completing hundreds of rotations per second, the centrifugal effect is enormous. It effectively reduces the gravitational compression at the star's center, lowering the central density and allowing the star to hold together, even though its total mass exceeds what a non-rotating star could support. How much extra mass can uniform rotation sustain? Theoretical calculations, which depend on the equation of state, suggest that uniform rotation can increase the maximum supportable mass by roughly 15 to 20% compared to the non-rotating limit. Some models predict increases up to about 25% at the most extreme physically achievable spin rates. To put this in concrete terms, if the non-rotating maximum mass is 2 solar masses, uniform rotation might allow a neutron star to support roughly 2.3 to 2.4 solar masses. If the non-rotating limit is 2.2 solar masses, uniform rotation could potentially extend the boundary to perhaps 2.6 or 2.7 solar masses. But here is the crucial thing about a supermassive neutron star. Its survival is conditional. It depends entirely on maintaining sufficient rotation. If the star slows down, if it loses angular momentum for any reason, the centrifugal support weakens. And if the rotation drops below the critical rate needed to sustain its particular mass, the star crosses from stability into collapse. A supermassive neutron star is alive but living on borrowed time. How much time depends on how quickly it loses angular momentum, which in turn depends on its magnetic field strength, whether it is emitting gravitational waves, and what environment surrounds it. The timescale could be seconds, minutes, hours, or potentially much longer. But unless something intervenes, the trajectory points in only one direction. The third category is the most extreme and the most short-lived. This is the hypermassive neutron star. A hypermassive neutron star contains so much mass that even rapid uniform rotation cannot support it. Its mass exceeds the maximum that any uniformly spinning neutron star can sustain, regardless of how fast it rotates. The only reason it hasn't collapsed is that it is rotating in a very special and inherently unstable manner. It is rotating differentially. To understand differential rotation, think about stirring a cup of coffee. When you stir, the liquid near the center of the cup spins faster than the liquid near the edges. Different parts of the fluid move at different angular speeds. That is differential rotation. Compare this to a spinning basketball, which is an example of uniform rotation. Every point on the basketball completes one full rotation in the same amount of time, moving as a single rigid body. A hypermassive neutron star does not rotate like a basketball. Its core is spinning much faster than its outer layers. Different shells of material at different distances from the center rotate at different rates. This differential rotation generates substantially more centrifugal support than uniform rotation could provide, particularly deep in the core where gravitational compression is greatest. The faster spinning core pushes outward with tremendous force, resisting collapse even when the total mass far exceeds the uniform rotation limit. Hypermassive neutron stars are born almost exclusively in the immediate aftermath of neutron star mergers. When two neutron stars smash together, the violence of the collision doesn't produce a neatly, uniformly rotating object. It produces a hot, turbulent, chaotic mass of ultra-dense matter where different regions are naturally spinning at wildly different rates. The merger itself imprints differential rotation as a natural consequence of its own violence. This configuration can temporarily support masses that would otherwise be completely unsustainable. A hypermassive neutron star might hold together with 30 to 50% more mass than the non-rotating Tolman Oppenheimer Volkoff limit, far beyond what even the fastest uniform rotation could handle. The differential rotation provides a vast reservoir of extra support. But differential rotation carries within it the mechanism of its own destruction. It is inherently and profoundly unstable. Several powerful processes work to eliminate it. An internal viscosity, essentially friction between layers of the rapidly churning ultra-dense fluid, acts to smooth out differences in rotation rate. The star's magnetic field, which can be amplified to extraordinary strengths during the turbulent merger, acts as an internal brake, coupling the different layers together and forcing them to rotate at the same speed. This magnetic braking is extremely efficient. It can convert differential rotation into uniform rotation on timescales measured in tens of milliseconds to perhaps a few hundred milliseconds. Within a span shorter than a single human heartbeat, the extra support keeping the star alive can be stripped away. Once differential rotation has been destroyed, the fate of the remnant hinges on its mass relative to the uniform rotation limit. If the remaining mass, after accounting for material ejected during the merger, falls below the maximum that uniform rotation can support, the remnant transitions from a hypermassive neutron star to a supramassive one. It is still above the non-rotating limit. It is still living on borrowed time. But instead of surviving for only milliseconds, it might now persist for seconds, minutes, hours, or potentially longer, gradually spinning down as it loses angular momentum through other mechanisms. If, however, the remaining mass still exceeds the uniform rotation limit, the loss of differential rotation leads to immediate catastrophe. With the extra support gone, nothing can prevent collapse. The transition from a hypermassive neutron star to a black hole can happen within a single millisecond. And there is a fourth possibility. If the combined mass of two merging neutron stars is so enormous that even differential rotation and thermal pressure together cannot support the remnant, then no intermediate neutron star phase exists at all. The merger produces a black hole directly and almost instantaneously, within less than a millisecond of the collision. The two neutron stars meet, and the combined mass is simply too overwhelming for any form of support to matter. We should also talk about the role that heat plays, because thermal pressure is the third and often overlooked pillar of temporary support. When a hypermassive neutron star is born in a merger, it is unimaginably hot. Temperatures in the interior can exceed 100 billion degrees, vastly hotter than the core of any normal star. This extreme thermal energy generates significant outward pressure, adding to the support provided by quantum mechanics and rotation. But this heat is fleeting. The newly born remnant cools primarily by emitting neutrinos, the ghostly subatomic particles that interact with matter only through the weak nuclear force and gravity. Because neutrinos interact so feebly, they can escape from the incredibly dense interior of the neutron star, where even photons are trapped. They carry away energy with extraordinary efficiency. In its first few seconds of existence, a newly formed merger remnant can radiate more energy in neutrinos than our sun will emit in its entire 10 billion year lifetime. This rapid cooling strips away the thermal contribution to the star's support, leaving the remnant increasingly dependent on rotation and degeneracy pressure alone. Which of these outcomes actually occurs in nature? Almost certainly all of them, depending on the masses of the merging neutron stars. The gravitational wave event detected in August of 2017 provided the first direct evidence that these processes happen in the real universe. The electromagnetic observations, the kilonova and its evolving afterglow, showed signatures consistent with a short-lived remnant that survived at least long enough to power the observed outflows of matter before eventually collapsing. But the precise lifetime of that remnant, whether it persisted for milliseconds, seconds, or longer, remains actively debated. Different research groups analyzing the same data have reached different conclusions, reflecting both the extraordinary difficulty of interpreting these events and the fundamental uncertainty in the equation of state. Theoretical studies have shown that the diversity of outcomes depends sensitively on the masses of the merging neutron stars. A system where both stars are relatively light, around 1.2 solar masses each, might produce a supramassive remnant that survives for an extended period, or even a permanently stable remnant if enough mass is ejected during the collision. A system where both are heavier, perhaps 1.5 solar masses each, is much more likely to produce a hypermassive remnant that collapses within milliseconds, or a direct collapse with no intermediate neutron star phase at all. And systems with large mass asymmetry produce yet different dynamics because the collision geometry and the patterns of mass ejection change. This brings us back to the fundamental uncertainty running through all of neutron star physics. We don't know the equation of state. We cannot yet say exactly how matter behaves at densities several times higher than those found inside atomic nuclei. And because of this, we cannot precisely calculate where the boundaries between these categories fall. Is the non-rotating maximum mass 2 solar masses, 2.2, 2.3? The answer shifts everything about which merger remnants survive and for how long. What we do know with confidence is the framework. General relativity imposes a maximum mass. Rotation can extend that maximum temporarily. Differential rotation extends it further, but only briefly. Accretion and mergers are the two primary pathways by which neutron stars gain mass. And when a neutron star's mass exceeds what its internal physics and rotation can support, the outcome is inevitable. The support will eventually fail. Whether this happens through the slow, patient process of accretion over millions of years, pushing a neutron star gram by gram toward its breaking point, or through the sudden violence of a merger that births a remnant already past the limit, the destination is the same. The only question is how long the journey takes. For a neutron star slowly accreting mass from a companion, the approach to the limit is gradual. Each gram of material brings it fractionally closer. And because accretion also spins the star up, the star might actually pass the non-rotating mass limit without collapsing, temporarily shielded by the rapid rotation it gained from the accretion process itself. The neutron star crosses a line it cannot see, protected by angular momentum it didn't know it needed. But if the accretion eventually stops, and the star begins to slow down through magnetic braking, it finds itself stranded above the non-rotating limit with steadily weakening rotational support. The approach to catastrophe in this scenario might play out over tens of thousands of years. Slow, inexorable, nearly invisible until the very end. For a merger remnant, the situation is compressed into moments. The remnant is born above the limit, hot and turbulent and spinning wildly, held together by supports that are already beginning to erode. Every millisecond that passes, it cools. Every fraction of a second, it loses angular momentum. The differential rotation that bought it time is being smoothed out by magnetic fields and viscosity. The thermal pressure that helped hold it up is bleeding away through neutrino emission. The trajectory from birth to collapse might be measured in milliseconds, or seconds, or minutes. But unless the remnant manages to shed enough mass to drop below the non-rotating limit, the direction is set. The supports are temporary. The time is borrowed. And the universe always collects. What happens when those supports finally give way? When the last reserves of rotational energy and thermal pressure are exhausted, and gravity's patience is rewarded, is where we go next. We've arrived at the most precarious moment in a neutron star's existence. The object has gained mass, either gradually through accretion over millions of years, or catastrophically through a merger that happened in a fraction of a second. It sits above the mass limit that its internal pressure alone can support. It is alive, but conditionally. Its survival depends entirely on rotation and, in some cases, on the residual heat from its violent birth. These are powerful supports, but they are not permanent, and the universe has mechanisms, patient and relentless, that will strip them away. This is the countdown, and once it begins, there is no way to stop it. Let's start with the most extreme case first. The hypermassive neutron star. This object was born moments ago in the collision of two neutron stars. It contains far more mass than any uniformly spinning neutron star could support. The only thing preventing its immediate collapse is differential rotation. The fact that its core is spinning much faster than its outer layers, generating a level of centrifugal support that uniform rotation alone could never provide. But differential rotation is unstable, profoundly unstable. It carries within itself the seeds of its own destruction, and those seeds begin to grow the instant the remnant is born. To understand why, think about what differential rotation really means inside an ultra-dense fluid. You have layers of neutron-rich matter rotating at different angular velocities. The inner core might complete one full rotation in less than a millisecond. The outer layers, though still spinning incredibly fast by any human standard, rotate measurably slower. There is a velocity gradient between these layers, a shearing motion where adjacent regions of matter slide past each other at different speeds. This shearing is unstable for two fundamental reasons. The first is viscosity. Even though neutron star matter is an exotic fluid unlike anything on Earth, it still has internal friction. Neutrons interact with each other through the strong nuclear force. At the extreme densities inside a merger remnant, these interactions are constant and powerful. When adjacent layers of fluid try to slide past each other at different speeds, these interactions resist the relative motion. They act like internal brakes, transferring angular momentum from faster spinning regions to slower spinning ones. The core tries to slow down. The outer layers try to speed up. Over time, the rotation profile smooths out, trending inexorably toward uniform rotation, where every part of the star spins at the same rate. The second and more powerful mechanism is the magnetic field. Neutron stars possess staggeringly powerful magnetic fields. An ordinary neutron star might have a surface magnetic field of roughly 1 trillion times the strength of Earth's magnetic field. But a freshly born merger remnant is even more extreme. During the collision, the violent turbulence and differential rotation amplify the magnetic field through a process called the magnetohydrodynamic dynamo. Think of it like wrapping and stretching a rubber band around a spinning rod. Each differential rotation of the core relative to the outer layers winds the magnetic field lines tighter, stretches them, amplifies them. Within milliseconds, the magnetic field can be amplified by factors of thousands, reaching strengths of 10,000 trillion times Earth's field or more. These amplified magnetic field lines act as internal couplings, connecting the faster spinning core to the slower spinning outer layers. They function almost like elastic bands stretched between the two regions. The tension in these wound-up field lines transfers angular momentum from the core to the envelope, breaking the core and accelerating the outer material. This magnetic braking of the differential rotation is extraordinarily efficient. Simulations suggest it can eliminate the velocity difference between the core and the outer layers in as little as 10 to a few hundred milliseconds. Let that sink in. The mechanism keeping a hypermassive neutron star alive can be destroyed in a time span shorter than the blink of a human eye. Within a tenth of a second, or at most a few tenths of a second, the differential rotation that was providing crucial extra support is smoothed out. The core is no longer spinning faster than the envelope. The star transitions from differential to approximately uniform rotation. And at that moment, the remnant faces a reckoning. If the mass that remains, accounting for whatever material was ejected during the merger, still exceeds the maximum that uniform rotation can support, then collapse is immediate. The uniform rotation cannot compensate. The centrifugal support is insufficient. there is nothing left to hold the star up. And gravity, which has been waiting patiently for this fraction of a second, takes over completely. If, however, enough mass was lost during the merger, and in the moments afterward, if material was flung outward by tidal forces and the turbulent dynamics of the collision, and the remaining mass falls below the uniform rotation threshold, then the remnant survives this first crisis. It transitions from hypermassive to supermassive. It is still above the non-rotating mass limit. It is still living on borrowed time. But instead of milliseconds, it now has potentially much longer. The supermassive phase is where the real drama unfolds on human comprehensible timescales. A supermassive neutron star might survive for seconds, minutes, hours, or potentially far longer. We do not know the exact timescales with certainty, and this uncertainty is not a failure of astrophysics, but a direct reflection of the unknowns in the equation of state and in the specific properties of each individual remnant. But we do know the mechanisms that are working to bring it down. They are slower than the ones that destroyed the hypermassive configuration, but they are just as inexorable. The first mechanism is magnetic dipole radiation. A spinning neutron star with a strong magnetic field is essentially a rotating magnet. A fundamental law of electromagnetism tells us that a changing magnetic field generates electromagnetic radiation. A spinning magnetic dipole radiates energy in the form of electromagnetic waves, primarily at the rotation frequency of the star. This radiation carries energy away from the spinning neutron star, and because the energy comes from the star's rotational kinetic energy, the star slows down. Magnetic dipole radiation is always present for any spinning magnetized neutron star. The rate at which it drains angular momentum depends on the strength of the magnetic field and the spin rate. A stronger magnetic field means more energy radiated per second, which means faster spin down. A faster spin also increases the radiation rate, but as the star slows, the rate decreases, creating a spin down that starts fast and gradually becomes slower over time. For a newly formed merger remnant with an extraordinarily strong magnetic field, the spin down from magnetic dipole radiation can be significant on timescales of seconds to minutes. For a neutron star spun up by accretion, which typically has a weaker magnetic field because the accretion process tends to bury and diminish the surface field, the spin down might play out over thousands or even millions of years. The second mechanism is gravitational wave emission. If the spinning neutron star is not perfectly symmetric, if it has some kind of lump, deformation, or oscillation mode that breaks its spherical symmetry, then it will radiate gravitational waves. These waves carry away both energy and angular momentum, causing the star to slow down. A freshly born merger remnant is almost certainly not perfectly symmetric. The violent collision leaves the remnant oscillating, vibrating, wobbling in complex patterns called quasi-normal modes. These oscillations can be quite large in the first moments after the merger. The remnant might be significantly deformed from a perfect sphere, with bulges and asymmetries that generate strong gravitational wave emission. As the oscillations damp out and the star settles into a more symmetric shape, the gravitational wave emission decreases. But in the early moments, it can be a powerful drain on the remnant's angular momentum. Even after the initial oscillations die down, there may be persistent deformations. The star's magnetic field, if it is strong enough and configured in certain geometries, can deform the star slightly, creating a small but permanent asymmetry that continuously generates gravitational waves. Some theoretical models suggest that mountains on neutron stars, deformations in the crust support by the extreme magnetic field or by crystalline structures in the outer layers, could sustain continuous gravitational wave emission for extended periods. These mountains are tiny by human standards, perhaps only a fraction of a millimeter tall on a star 20 kilometers across. But at neutron star densities, even a fraction of a millimeter represents an enormous amount of mass shifted away from perfect symmetry. The third mechanism is the interaction between the neutron star's magnetic field and the surrounding material. After a merger, the neutron star is not sitting in empty space. It is surrounded by a cloud of ejected material, debris from the collision that didn't escape entirely. Some of this material falls back toward the star. Some of it forms a disk. The magnetic field lines of the star extend outward into this surrounding material, coupling the star's rotation to the motion of the environment. When the magnetic field lines thread through surrounding matter that is moving slower than the star is spinning, they act as a brake. They transfer angular momentum from the star to the surrounding material, slowing the star down and pushing the material outward. This is the same mechanism that causes the solar wind to carry angular momentum away from our sun, but enormously amplified by the neutron star's vastly more powerful magnetic field. The fourth mechanism, specifically important for merger remnants, is neutrino cooling. A freshly formed merger remnant is fantastically hot. The temperatures in its interior can exceed 100 billion degrees, far hotter than the core of any ordinary star. At these temperatures, the thermal energy of the matter contributes significantly to the outward pressure supporting the star. This thermal pressure is a genuine and important part of what holds the remnant up, particularly in the earliest moments of its existence. But this heat is radiating away. Neutrinos, those ghostly particles that barely interact with anything, are streaming out of the neutron star's interior at a prodigious rate. Neutrinos are produced in abundance at these temperatures through a variety of nuclear reactions, and because they interact so weakly with matter, they can escape the incredibly dense interior, where even photons are trapped and scattered endlessly. The neutrinos carry thermal energy out of the star, cooling it from the inside. The rate of neutrino cooling is extreme. In the first few seconds after a merger, the energy lost through neutrino emission alone can vastly exceed the total luminosity of all the stars in a galaxy combined. The remnant is losing its thermal energy at an almost incomprehensible rate. As it cools, the thermal contribution to the outward pressure decreases. The support structure weakens. Thermal pressure alone doesn't usually make the difference between survival and collapse, but it contributes, especially for a remnant that is right on the edge, where the mass is only marginally above what rotation alone can support. The loss of thermal pressure can be the final nudge that pushes the remnant past the point of no return. So here is the picture. A supermassive neutron star sits above the non-rotating mass limit, supported by its rapid spin and possibly by residual thermal pressure. Magnetic dipole radiation is steadily draining its rotational energy. Gravitational waves from asymmetries are sapping additional angular momentum. The magnetic field interacting with surrounding material is breaking its rotation further, and neutrino emission is cooling it, eroding the thermal contribution to its support. Each of these mechanisms works continuously. Some are faster than others. Some dominate at different stages of the remnant's life, but all of them push in the same direction. They all work to reduce the supports that are keeping the star alive. and none of them can be reversed. There is no mechanism that will spin the star back up or reheat it once these processes are underway. The arrow points one way, the clock runs in one direction. As the rotation slows and the thermal energy dissipates, the centrifugal support at the star's center weakens, and this is where a devastating feedback loop begins. With less centrifugal support, the core is no longer held outward as effectively. Gravity, which never weakened, begins to compress the core further. The central density starts to rise. The matter at the very center of the star, already at densities several times higher than the inside of an atomic nucleus, gets squeezed even denser. Now, recall what we discussed earlier about general relativity. At these extreme densities, pressure itself is a source of gravity. As the core compresses and the density rises, the matter responds by increasing its pressure to resist the compression. But in doing so, the increased pressure adds to the gravitational field, which strengthens the inward pull, which demands even more pressure, which adds more to gravity, which compresses the core further. This is a feedback loop. And once the star has lost enough rotational support, once its spin has dropped below a critical rate, this loop becomes self-reinforcing and uncontrollable. The core density doesn't just rise, it accelerates. Each small increase in density leads to a slightly larger increase in the next instant. The process feeds on itself, running away from equilibrium with increasing speed. And here's where the equation of state uncertainty we discussed earlier becomes not just an academic question, but a matter of life and death for the neutron star. Remember that earlier we described the possibility that exotic forms of matter might lurk in the cores of the most massive neutron stars. Quark matter, hyperons, kaon condensates. These exotic phases were introduced as possibilities for stable neutron stars, things that might exist in equilibrium deep inside the densest cores. But now, as the central density is climbing relentlessly during the approach to collapse, those possibilities become something far more dangerous. As the density rises beyond the values found in a stable neutron star, the matter may undergo phase transitions. The neutrons, squeezed beyond their limits, might begin to dissolve into their constituent quarks, or heavy particles called hyperons might appear, particles that are normally too massive to exist, but which become energetically favorable at extreme compressions. These phase transitions tend to soften the equation of state. That means the matter yields more easily under pressure at precisely the moment when it needs to resist, more aggressively than ever before. Think about what this implies. The density is rising because support is weakening. The feedback loop is already engaged. And now, on top of that, the matter itself may be undergoing a fundamental change in character that makes it less resistant to further compression. It is as if the dam we described is not only facing rising water, but is simultaneously having its structural materials weaken from within. The flood and the structural failure happen together, each one accelerating the other. Whether these phase transitions actually occur and at what density they kick in depends entirely on the equation of state. This is exactly why the equation of state matters so profoundly. It doesn't just set the maximum mass, it determines how the matter behaves during the final moments of the countdown, whether it stiffens and resists or softens and yields. And we do not yet know the answer. Let me try to convey what this feels like from inside the star, though of course nothing could survive to observe it. For potentially millions of rotations, the star has been spinning, slowly losing energy, slowly slowing down. Each rotation takes fractionally longer than the last. For a long time, the changes are imperceptible. The star is losing angular momentum, but it still has plenty. The central density is rising, but gradually. The equilibrium is shifting, but not dramatically. From the outside, if you could somehow monitor the star, you would see it spinning down slowly, radiating energy, behaving like a well-understood astrophysical object. Patient, predictable. Then something changes. The spin rate drops below a threshold that depends on the star's specific mass and the equation of state. And suddenly, the gradual process is no longer gradual. The feedback loop engages. The central density begins rising faster than the star can respond. The equilibrium that the star had been maintaining, the careful balance between gravity and all its opposing forces, starts to slip. Not slowly, but with accelerating urgency. What makes this so treacherous is that the transition from stable to unstable can be sharp. Think of a dam holding back water. As long as the dam holds, everything seems fine. The water level can rise gradually. The pressure on the dam increases steadily. But there is a critical point where the dam's structural integrity is exceeded. And when that happens, the dam doesn't develop a small leak that gets slightly worse. The dam fails catastrophically. The transition from holding to breaking happens over a timescale far shorter than the time it took the water to rise. A neutron star approaching collapse behaves similarly. The spin down is gradual. The approach to the critical threshold is steady and potentially very long. But once the threshold is crossed, the collapse is not gradual. The feedback loop accelerates the process until it becomes unstoppable within fractions of a second. We need to emphasize something critical here. Physicists cannot predict exact lifetimes for these objects with any precision. The uncertainty in the equation of state, the unknown internal composition, the variability in magnetic field strengths and geometries, the uncertain initial conditions after each individual merger, all of these combine to create an enormous range of possible timescales. A supermassive neutron star born from a merger with a mass only slightly above the non-rotating limit, spinning very rapidly with a relatively weak magnetic field, could potentially survive for minutes, hours, or conceivably much longer. The spin down would be slow. The margin of safety would be relatively large. It would take a long time for the rotation to drop to the critical level. Conversely, a supermassive remnant with a mass much closer to the uniform rotation limit, spinning near the minimum rate needed to sustain itself, with a powerful magnetic field that drains angular momentum quickly, might collapse within seconds of transitioning from the hypermassive phase. And for neutron stars that approach the limit through slow accretion rather than a merger, the timescales are entirely different. An accreting neutron star in a binary system might cross the non-rotating mass limit without even noticing, because the accretion process simultaneously spins it up. It could persist as a supramassive neutron star for millions of years, slowly gaining mass and slowly spinning faster, with the two effects roughly balancing each other. But if the accretion eventually stops, if the companion star is fully consumed or the binary is disrupted, the neutron star finds itself stranded above the non-rotating limit, with no new angular momentum being supplied. From that point, the spin down begins, driven by magnetic dipole radiation and possibly gravitational wave emission. And the approach to collapse plays out over thousands to millions of years instead of seconds. Consider how strange and eerie this scenario truly is. For millions of years, the neutron star was gaining mass and gaining spin simultaneously. The accretion fed both its danger and its defense at the same time. The star grew heavier, creeping toward the limit, but it also spun faster, raising the effective limit just enough to stay ahead of disaster. From the outside, it looked like a normal millisecond pulsar, a spinning, pulsing, radiating beams of radio waves with metronomic precision. Nothing in its outward appearance would betray the fact that it had already crossed the non-rotating mass limit, that it was already, in a sense, living beyond its means. Then the accretion stops. Perhaps the companion star has been fully stripped of its outer layers, reduced to a white dwarf or a helium core too small to fill its Roche lobe. Perhaps the binary was disrupted by a close encounter with another star. Whatever the cause, the supply of new mass and new angular momentum ceases. And now, the neutron star is alone. It doesn't notice immediately. It is still spinning hundreds of times per second. It still has enormous reserves of angular momentum. But those reserves are finite, and they are being drained by the same mechanisms that drain every spinning magnetized neutron star. Magnetic dipole radiation, possible gravitational wave emission from tiny asymmetries. With each passing century, the spin rate drops by a barely measurable amount. With each passing millennium, the central density creeps upward by an imperceptible fraction. Tens of thousands of years pass, hundreds of thousands. The neutron star spins down in the dark, patient and oblivious, while the margin between its current spin and the minimum spin needed for survival slowly, silently closes. By the time the threshold is finally crossed, no one is watching. The collapse, when it comes, is sudden and silent. Whether the countdown takes a fraction of a second or a million years, the physics is the same. The central density rises as support weakens. The feedback loop between pressure and gravitational contribution engages. And there comes a moment when the core density reaches a point beyond which no stable configuration exists. What happens at that moment? The matter in the core is being compressed beyond the density at which any known or theorized force can maintain equilibrium. The neutrons, which have been resisting compression through degeneracy pressure and nuclear repulsion, can no longer push back hard enough. Every additional increment of pressure generates more gravity than it provides resistance. The equation of hydrostatic equilibrium, the mathematical expression that describes the balance between gravity and pressure inside a star, ceases to have a solution. There is no arrangement of matter, no possible distribution of pressure and density that can hold the star up. This is not like the core running out of fuel, as happens in a normal star approaching a supernova. The fuel, in a sense, was always the rotation and the thermal energy, and those have been slowly exhausted. But more precisely, this is about the fundamental geometry of space-time. The curvature has become too extreme. The density has exceeded a threshold set by general relativity itself. And general relativity is not forgiving. It does not allow exceptions. It does not permit second chances. Think about what the matter is experiencing in these final moments. For the entire lifetime of the neutron star, whether that lifetime was millions of years or a few seconds, there was always a solution. Always a way for the forces to balance. The star might have been precariously balanced, teetering on the edge, but the edge was always there. There was always a ledge to stand on. Now, the ledge is gone. The density at the center has crossed beyond the last possible equilibrium point. And the response is not a gentle slide into a slightly denser state. It is a free fall, an implosion. The central regions of the star begin to compress inward at velocities that approach a significant fraction of the speed of light. The matter, which has been pushing back against gravity for its entire existence, suddenly finds that pushing back only makes things worse. More pressure means more gravity. More resistance means stronger collapse. The harder it fights, the faster it falls. What makes this different from any other collapse in nature is that there is nothing waiting at the bottom. When a normal star's core collapses in a supernova, the collapse is halted when the matter reaches nuclear density and the strong force provides a floor. The core bounces and a neutron star is born, but here, the matter is already at nuclear density and beyond. There is no new force waiting to intervene. There is no new floor. There is no bounce. The collapse continues past every density milestone, past every threshold, because there is no known physics that can provide a new equilibrium. The matter in the core is falling inward at a significant fraction of the speed of light. The density is climbing exponentially. The curvature of space-time is increasing without limit. And at some point during this implosion, something extraordinary happens. The curvature of space-time becomes so extreme in the collapsing core that a surface forms. Not a physical surface made of matter, but a mathematical surface defined by the geometry of space-time itself. A surface where the curvature is so intense that nothing, not matter, not light, not any form of energy or information, can travel outward across it. This is the event horizon. And its formation marks the death of the neutron star and the birth of something entirely new. Something from which there is no return. The final moments of that transition, the brief and violent act of becoming a black hole, is where our story reaches its climax. The ledge is gone. The central density has crossed beyond the last possible equilibrium point. And now, deep inside the collapsing core of what was, moments ago, a neutron star, something begins to form that will change the nature of this object forever. Let's walk through what happens. Not in vague terms, not in metaphors, but as precisely as our understanding of general relativity allows. Because the death of a neutron star and the birth of a black hole is one of the most extraordinary transitions in all of nature. And it happens with a speed and a finality that is almost difficult to believe. The collapse of the core, once it begins in earnest, proceeds at a breathtaking pace. The central regions are falling inward at velocities reaching tens of percent of the speed of light. Matter that moments ago was held in equilibrium, balanced between gravity and the combined forces of quantum mechanics and nuclear physics, is now in free fall. There is no force acting to slow it down. Every mechanism that could resist gravity has already been overwhelmed. The degeneracy pressure, the nuclear repulsion, even the additional support from rotation and thermal energy, all of it has been rendered insufficient by the runaway feedback between pressure and gravitational contribution that we described earlier. In these final fractions of a second, the density at the center of the collapsing core is climbing at an exponential rate. Material that was already denser than an atomic nucleus is being compressed to densities 2, 3, 5, 10 times higher. The curvature of space-time in this region is increasing without any known bound, and at some point during this implosion, a critical threshold is crossed. The curvature of space-time in the collapsing core becomes so extreme that a trapped surface forms. This is a closed two-dimensional surface, roughly spherical, inside which the curvature of space-time is so intense that all paths, even paths traveled by light, curve inward. Nothing inside the surface can move outward, not matter, not light, not any signal or particle or form of energy. Every possible trajectory from inside this surface leads further inward, deeper into the collapsing core. Outward simply ceases to exist as a direction. The geometry of space-time itself has folded in on the collapsing matter, sealing it off from the rest of the universe. This trapped surface is the seed of the event horizon. It forms first deep inside the collapsing core, encompassing only a tiny fraction of the total mass. At the moment of its formation, it might be incredibly small, perhaps only a few kilometers across or even smaller, but it grows. As more matter falls inward across this surface, the trapped region expands. The event horizon sweeps outward through the collapsing star, engulfing more and more material with each passing millisecond. The growth of the event horizon is rapid, but not instantaneous. It takes a finite amount of time for the horizon to expand from its initial seed size to encompass the bulk of the neutron star's mass. The exact time scale depends on the mass and the dynamics of the collapse, but it is measured in milliseconds, perhaps 1 millisecond, perhaps a few. Within this extraordinarily brief window, the event horizon grows from a point deep in the core to a surface roughly proportional to the mass it has swallowed. For a neutron star collapsing to form a black hole with a mass of about 2 to 3 times the mass of our Sun, the final event horizon would have a radius of roughly 6 to 9 kilometers. Think about that for a moment. The neutron star itself was about 10 to 12 kilometers in radius. The event horizon that replaces it is of comparable size but represents something fundamentally different. The neutron star was a physical object made of matter, held up by forces, observable in principle from the outside. The event horizon is not a physical surface. It is a boundary in space-time. There is nothing there you could touch, nothing you could stand on. No wall, no membrane, no barrier made of any substance. It is simply the mathematical surface beyond which the curvature of space-time prevents anything from escaping. If you were falling inward and crossed the event horizon, you would not feel it happen. There would be no bump, no flash, no sign. The local physics around you would seem perfectly normal, but you would have crossed a point of no return. From that moment forward, no matter what you did, no matter how powerful your rockets, no matter how fast you tried to move, you would be inexorably drawn deeper inward. The event horizon is not a thing. It is a consequence of geometry. The size of the event horizon is determined by the mass of the black hole. For a non-rotating black hole, the relationship is remarkably simple. It was first calculated by the German physicist Karl Schwarzschild in 1916, just months after Einstein published his general theory of relativity. For a black hole with the mass of our Sun, the event horizon radius, called the Schwarzschild radius, would be about 3 kilometers. For a black hole with twice the Sun's mass, it will be about 6 kilometers. 3 times the Sun's mass, about 9 kilometers. The relationship is linear. Double the mass, double the radius. But the black holes formed from collapsing neutron stars are almost certainly rotating. The neutron star was spinning before it collapsed, and angular momentum is conserved during the collapse. The spin doesn't disappear. It gets compressed along with everything else. The resulting black hole is what physicists call a Kerr black hole. named after the New Zealand mathematician Roy Kerr, who found the solution to Einstein's equations for rotating black holes in 1963. A Kerr black hole has a slightly different structure than a non-rotating one. Its event horizon is somewhat smaller for the same mass, and the space-time around it is dragged into rotation by the spin, creating a region outside the event horizon called the ergosphere, where space-time itself is pulled along with the rotation. But the key point is the same. Once the event horizon has formed and grown to encompass the bulk of the collapsing mass, the neutron star is gone. Not hidden, not compressed into a smaller form. Gone. The matter that made up the neutron star, all those neutrons, all those quarks, all that degeneracy pressure and nuclear repulsion, none of it exists as a distinct physical structure anymore. It has fallen behind the event horizon into a region of space-time from which no information can escape. The black hole that remains is described entirely by just a few properties. Its mass, its spin, and its electric charge, which for astrophysical black holes is effectively zero. Everything else about the original neutron star, its temperature, its composition, its internal structure, the equation of state of its matter, all of that information is hidden behind the event horizon, inaccessible to the outside universe. This is sometimes called the no-hair theorem, the idea that black holes have no distinguishing features beyond mass, spin, and charge. All the complexity of the neutron star, all the rich nuclear physics that we spent so long discussing, is erased, replaced by the simplest object in all of general relativity. But the collapse of the neutron star into a black hole is not a perfectly clean process. Not everything falls neatly behind the event horizon, and the material that doesn't fall in immediately is responsible for some of the most spectacular observable phenomena in the universe. During the final collapse, the outer layers of the neutron star are not all moving inward at the same rate. Material near the rotational equator has more angular momentum than material near the poles. As the core collapses and the event horizon forms, this equatorial material can be flung outward or remain in orbit around the newly formed black hole rather than falling in directly. The result is that the black hole is born surrounded by a disk of ultra-dense, ultra-hot material, an accretion disk composed of neutron-rich matter that didn't quite make it past the event horizon during the initial collapse. This accretion disk is transient. It won't last forever. The material in the disk will gradually spiral inward, losing angular momentum through viscous friction and magnetic interactions, eventually crossing the event horizon and adding to the black hole's mass. But in the moments after the collapse, this disk can contain a significant fraction of a solar mass of material, and it is incredibly hot and energetic. In the case of a neutron star merger, the situation is even more complex. The collision of two neutron stars, regardless of whether the remnant survives for milliseconds or minutes before collapsing, ejects substantial amounts of material. Tidal forces during the final inspiral rip matter from the surfaces of both neutron stars. The collision itself launches shockwaves that blast material outward at significant fractions of the speed of light. And any disk that forms around the merger remnant or around the final black hole can drive winds that carry additional matter away from the system. This ejected material is extraordinarily important for the universe's chemistry. Because it is made of neutron-rich matter at extreme densities, it provides ideal conditions for the rapid neutron capture process responsible for creating many of the heaviest elements in the periodic table. As we discussed earlier, gold, platinum, uranium, and dozens of other heavy elements are forged in these outflows. A single neutron star merger can produce several times the mass of Earth in pure gold and several times more in platinum. These elements are scattered into interstellar space, eventually mixing with gas clouds that collapse to form new stars and planets. The heavy elements in our own solar system, the gold in Earth's crust, the uranium in its interior, were almost certainly produced in one or more ancient neutron star mergers that occurred in the galaxy billions of years before our sun was born. But let's return to the moment of the collapse and ask a critical question. Can we observe it? Can we detect the transition from neutron star to black hole? The answer is yes, at least in principle, and several distinct types of signals carry information about what happened. The first and perhaps most direct signal is gravitational waves. As we discussed, the merger of two neutron stars produces a powerful gravitational wave signal, the rising chirp that was detected for the first time in August 2017. But the gravitational wave signal doesn't end at the moment of collision. If the merger produces a neutron star remnant that survives for any period of time before collapsing, that remnant emits its own gravitational waves. A rapidly spinning, oscillating neutron star radiates gravitational waves at frequencies determined by its size, mass, and internal structure. These post-merger gravitational waves would carry direct information about the equation of state, about what matter does at extreme densities, information that would help resolve one of the biggest open questions in physics. When the remnant finally collapses into a black hole, the gravitational wave signal changes abruptly. The oscillation frequencies of a neutron star are replaced by the quasi-normal modes of a black hole, the characteristic vibrations of space-time itself around the newly formed event horizon. This transition is called the ring down, by analogy with the way a bell vibrates at specific frequencies after being struck. A newly formed black hole rings at frequencies determined entirely by its mass and spin, gradually settling into a quiescent state as the vibrations are radiated away as gravitational waves. Detecting the transition from neutron star oscillation to black hole ring down in a gravitational wave signal would be extraordinary. It would tell us the moment of collapse, the mass and spin of the resulting black hole, and the properties of the neutron star in its final moments. Current gravitational wave detectors have not yet achieved the sensitivity needed to reliably detect these post-merger signals, but next-generation detectors being planned and built are expected to reach the required sensitivity within the next decade or two. When they do, we will have a direct window into the moment a neutron star dies. The second type of signal is electromagnetic. When the black hole forms and accretes matter from the surrounding disk, the conditions near the event horizon can drive relativistic jets, narrow beams of matter and energy accelerated to speeds very close to the speed of light. If one of these jets happens to point toward Earth, we observe it as a short gamma ray burst, an intense flash of gamma radiation lasting from a fraction of a second to a few seconds. Short gamma ray bursts have been observed for decades, but their origin was debated for years. The detection in August 2017 provided the first definitive confirmation that at least some short gamma ray bursts are produced by neutron star mergers. The gravitational wave signal from the merger arrived at Earth about 1.7 seconds before a short gamma ray burst was detected by orbiting gamma ray telescopes. The two signals came from the same direction in the sky, confirming the connection between neutron star mergers and short gamma-ray bursts. However, we need to be cautious about how much we can infer from these electromagnetic signals. The gamma-ray burst from the 2017 event was unusually faint, suggesting the jet was not pointed directly at Earth, but was viewed from an angle. The brightness and duration of a gamma-ray burst depend heavily on the viewing angle, the amount of material surrounding the system, and the specific dynamics of the jet formation. These variables make it difficult to extract precise information about the moment of collapse from the gamma-ray signal alone. The third type of signal is neutrinos. During the final moments of a neutron star's existence, as the core compresses beyond stability and the event horizon forms, the collapsing matter emits a burst of neutrinos. These neutrinos are produced by the extreme nuclear reactions occurring in the rapidly densifying material. Unlike photons, which are trapped by the dense matter surrounding the collapse, neutrinos can escape because they interact so weakly with matter. A burst of neutrinos from a nearby neutron star collapse could potentially be detected by neutrino observatories on Earth, providing information about the moment of collapse and the conditions in the final instance of the neutron star's existence. However, neutrinos are extremely difficult to detect because they interact so rarely with ordinary matter. The neutrino signal from a neutron star collapse would be detectable only if the event occurred relatively nearby, within our galaxy or perhaps in a very nearby galaxy. For events at the distance of the 2017 detection, roughly 130 million light-years, the neutrino flux at Earth would be far too faint to detect with current or planned neutrino observatories. So, in practice, our best window into the moment of collapse comes from gravitational waves, supplemented by electromagnetic observations when available. The combination of multiple types of signals, gravitational waves, gamma rays, optical and infrared light from the kilonova, radio waves from the afterglow, and potentially neutrinos, is called multi-messenger astronomy. It is one of the most exciting frontiers in modern astrophysics, and neutron star mergers are among its primary targets. But we must be honest about what we do not know. The precise lifetime of a merger remnant before collapse remains deeply uncertain. Different theoretical models, using different equations of state, predict lifetimes that differ by orders of magnitude. Some models predict that the remnant from the 2017 event collapsed within a few milliseconds. Others argue it survived for hundreds of milliseconds or even seconds. A few have suggested it might have survived indefinitely, shedding enough mass during the merger to drop below the permanent stability limit. The observational data constrain these possibilities, but do not yet decisively distinguish between them. This uncertainty is not a weakness. It is a sign that we are working at the very frontier of knowledge, in a regime where the fundamental physics of matter is not yet fully understood. Every new detection of a neutron star merger, every new mass measurement of a heavy neutron star, every improvement in gravitational wave detector sensitivity brings us closer to resolving these questions. The equation of state, that mysterious relationship between density and pressure at extreme conditions, is being slowly pinned down by observations. And as it comes into focus, so will our understanding of exactly when, how, and why neutron stars collapse. Let's step back now and take in the full picture, because tonight we have followed a remarkable journey. We began with a neutron star, one of the most extreme objects in the universe. An object containing more mass than our sun, compressed into a sphere smaller than a city. We explored the forces that hold it up. The quantum mechanical pressure of neutrons refusing to share the same quantum state. The repulsive power of the strong nuclear force at extreme densities, and the strange and counterintuitive prediction of general relativity that pressure itself contributes to gravity, creating a hard ceiling on how much mass any neutron star can support. We saw that this ceiling, the Tolman Oppenheimer Volkoff limit, is not one fixed number. It depends on the equation of state of ultra-dense matter, on physics we have not yet fully solved. Different theoretical models place the non-rotating limit somewhere roughly between 2 and about 2.5 solar masses. Observations of real neutron stars have narrowed this range, ruling out the softest equations of state, but a definitive answer remains beyond our current reach. We followed the two paths by which a neutron star can approach and exceed this limit. The slow path of accretion, where matter from a companion star drips onto the neutron star over millions of years, patiently adding mass while simultaneously spinning it up. And the violent path of a merger, where two neutron stars collide and create a remnant that may be born well above the non-rotating limit. Supported temporarily by differential rotation and heat. We learned to distinguish three categories of neutron star based on mass and rotation. Ordinary neutron stars, permanently stable below the non-rotating limit. Supermassive neutron stars, above the non-rotating limit but sustained by rapid uniform spin. And hypermassive neutron stars, so massive that even uniform rotation cannot support them, kept alive only by the inherently unstable differential rotation imprinted by the violence of their birth. We watch the mechanisms that erode temporary support. Magnetic braking that destroys differential rotation in milliseconds. Magnetic dipole radiation that gradually slows the spin over longer timescales. Gravitational wave emission that drains angular momentum from any asymmetry. Neutrino cooling that bleeds away thermal energy. All of these mechanisms push relentlessly in one direction, weakening the supports that keep the star from collapsing. We followed the feedback loop that engages when support drops below a critical threshold. The central density rises. Pressure increases to resist the compression. But increased pressure adds to gravity, which demands more pressure, which adds more gravity, a runaway that accelerates beyond any possibility of recovery. And we witness the final transition, the formation of an event horizon deep inside the collapsing core. Its rapid growth as it engulfs the bulk of the neutron star's mass. The birth of a black hole, described by nothing more than its mass and spin, all the complexity of the original neutron star erased behind a boundary from which no information can escape. And we saw that not everything disappears instantaneously. Material forms disks, gets ejected, carries heavy elements into the galaxy, and produces spectacular observable signals in gravitational waves, gamma rays, and light. The story of a neutron star becoming too heavy to survive is ultimately a story about limits, about the boundaries that physics imposes on matter and energy and space-time. There is a maximum mass, there is a maximum density. There is a threshold beyond which no force in nature can maintain equilibrium. These limits are not arbitrary. They emerge from the deepest principles of quantum mechanics and general relativity. They are written into the structure of the universe itself. But within those limits, there is room for extraordinary complexity, for borrowed time, 4 objects that exist on the edge, sustained by mechanisms that are brilliant in their physics and temporary in their duration. The universe permits these precarious states. It allows neutron stars to survive above the non-rotating limit, spinning furiously, radiating energy, teetering on the boundary between existence and annihilation. It gives them seconds, or minutes, or years, or millennia. But it always collects. The support always fades, the spin always slows, the density always rises, and eventually, inevitably, gravity wins. What we're left with is a profound appreciation for the delicate balance that governs the most extreme objects in nature. A neutron star's fate depends not on one single variable, but on a web of interconnected factors. Its total mass, its rotation rate, its temperature, its magnetic field strength, the equation of state of its internal matter, which remains one of the most important unsolved problems in modern physics. Change any one of these, and the outcome can shift from permanent survival to delayed collapse to immediate annihilation. There is no single magic number that separates life from death for a neutron star. The boundary is a surface in a multi-dimensional space of physical parameters. It shifts depending on rotation, composition, thermal state, and the fundamental behavior of matter at densities we cannot yet reproduce in any laboratory. And that is not a failure of our understanding. That is the frontier. The boundary where known physics meets the unknown, where observation meets theory, where the densest objects the universe can create before they cease to be objects at all, push our understanding to its absolute limits. Somewhere out there, right now, in a galaxy we may never observe, a neutron star is approaching its limit. Perhaps it is accreting matter from a companion, slowly growing heavier over millions of years. Perhaps it is the freshly born remnant of a merger, vibrating and glowing and spinning furiously in the aftermath of a collision that happened moments ago. Perhaps it is a supermassive neutron star that has been spinning for thousands of years, gradually slowing, gradually approaching the threshold beyond which no equilibrium is possible. And at some point, in some place, the support will fail. The density will rise beyond the last stable point. The curvature of space-time will fold inward, forming a surface from which nothing returns. A neutron star will die, and a black hole will be born. It is happening somewhere in the universe right now. It has happened countless times before. It will happen countless times again. And each time it does, it carries with it the same message: that the universe has rules, that those rules have limits, and that when those limits are exceeded, the consequences are absolute, irreversible, and final. The neutron star is gone. In its place, a black hole sits quietly in the dark, carrying the mass, carrying the spin, but carrying nothing else. No memory of what it was. No trace of the forces that fought to hold it together. No echo of the matter that once resisted gravity with everything quantum mechanics and nuclear physics could muster. Just a region of curved space-time, silent and permanent, where a star used to be. And that, in the end, is what happens when a neutron star becomes too heavy to survive.